For the last 10 years, touching a smartphone screen meant interacting with dead pixels. You tapped a flat shape, and it changed color. There was no physical mass to these interfaces, no depth. We operated entirely on a two-dimensional plane. Look at this presentation from the initial rollout of the flat aesthetic. Notice the textureless typography and the complete absence of shadows. We forced users to navigate interfaces using pure memory, because there was no way to physically distinguish a static document from an interactive button. At WWDC 2026, Apple discarded UIKit and introduced a replacement framework. They call it Liquid Glass. It is a live, physical simulation. This is a mandatory, system-wide physics engine running constantly in the background of iOS 26. Every tab bar, navigation element, and control overlay now operates as a continuous optical illusion. For developers, this means the toolkit has changed. Success in iOS 26 depends on a transition from drawing static views to configuring a live environment governed by simulated mass. This diagram illustrates the new z-axis. Instead of a standard isotropic blur, which simply scatters underlying pixels to create a frosted effect, Liquid Glass uses a process called lensing. Notice how the glass node physically bends simulated light rays as they pass through it. As those light rays travel upward, the material absorbs the color values of the environment beneath it. Surface hue and the depth of shadows are calculated in real time, based on whatever media is scrolling underneath. The material is also elastic. When a user presses the screen, the system calculates the coordinate and pressure data, generating a localized glow that radiates directly from the point of contact. By combining real-time lensing, environmental color bleed, and elastic responses, the hardware tricks the human brain. Your optical processing system registers the digital interface using the exact same intuition we apply to real objects. Apple mandates a strict architectural division to support this illusion. They split the screen into two zones: the content layer, which holds your documents and media, and the functional layer, which holds your interactive controls. Liquid Glass belongs exclusively in the functional layer. If you place a glass element on a static flat background in the content layer, there is nothing for the light rays to refract. The physics engine renders a dull, tinted rectangle instead of a dynamic material. Summoning this optical engine requires exactly one line of SwiftUI code. You define the variant, define the shape, and the system handles the lighting calculations. This animation demonstrates the GlassEffectContainer. When multiple glass elements share the screen, placing them in this container groups their rendering into a single visual pass. Because they share a coordinate space, as two shapes approach, their edges stretch and merge into a unified form. Today, developers are already pushing these boundaries. By extracting the raw vector paths of core text glyphs and feeding them directly into the glass modifier, you can turn typography itself into refractive liquid glass. That single line of code hides massive GPU complexity. Success now depends on engineering physical spacing and mass rather than simply arranging a grid. Simulating realistic physics and software carries a biological risk. The elastic, morphing transitions of liquid glass can cause severe motion sickness and vestibular disorientation in certain users. Developers carry the responsibility to intercept system preferences and disable those kinetic transitions. Wrapping your animations in the accessibility reduce motion environment variable is a strict requirement. If you treat this update as a simple visual reskim, the result will be a disorienting, physically uncomfortable application. iOS 26 attempts to align digital interaction with human instinct. By simulating optical reality, the system lets us navigate software using the same physical intuition we use for real-world objects. Building for this platform now requires a mastery of digital material science. Success depends on understanding how light and mass behave in a virtual environment.